Well, hello. This is classwork number 3, working with square roots. And so I'm going to go through this pretty quickly. If I go through too quickly or leave something unanswered, please ask me in class. You're also welcome to shoot me an email. So if you ever need to, say you're on a problem at home or even in class, maybe you're too shy, maybe you don't know me that well, you think I might get upset if you ask a question, it's okay. You can always email me right here, okay? On the problem. It'll even tell me what problem you're working on. You could say, hey, could you just go over this in class? Maybe you don't want to be called out. Maybe, for all kinds of reasons. Please use this resource with any questions you might have. It might not even be about this problem. You could just ask me a general question. You can ask me anything you want, okay? So with this first problem, I'm just going to go through and solve all these 10 problems. There's a few rules we should be aware of. So one is that we can rewrite this as one radical because these are both square roots. So we're going to have 160 divided by 2. The square root of 2 is not a perfect square, and we could simplify 160 and pull out a square root of 2 and the cap and cancel out. It's a lot easier, though, if we do division first. And I know that's kind of strange. People are like, oh, wait, isn't a radical the same thing as an exponent? And don't you have to do exponents before you do division? Technically, yes. But the way that this is written is that you have exponents that they fall into the same, you have the same, what am I trying to say? You have different bases, the same exponent, but they're being divided. So you can perform the division first. And if you want, you can solve it the other way. You can pull out a square root of 2. So what is 160 divided by 2? 80. So you have the square root of, if I pull the 2 out, I'll have 80 times the square root of 2, because 2 times 80 is 160. And then divided by the square root of 2, and those 2's would cancel out. So that's the same thing as dividing first and getting the square root of 80. So either way, we have the square root of 80. That's what we have to simplify. And then I'll erase some of this. Make myself more room. Woo! Alright. Square root of 80. So we're going to break it up. I'm just going to pull off, well, usually, so if it's even, I usually try to divide by the smallest number, like a 2. I know this has lots of 2's in it, so instead of going really far down, I'm going to kind of make it a wider tree. Just say 8 and 10. And then this 10 is 5 and 2, or 2 and 5. This is going to be 4 and 2. Now, I know that 4 is a perfect square, so I'm going to square root that. Square root of 4 is 2. And then I have another perfect square. I have this 2 and that 2. So together those make another 4, so that 4 also squares to a 2. And I'm left with a 5 behind. So this will be my answer. Those 2's come back together, though, to make a 4. So 4 square root 5 will be my answer. Okay, that'll be the answer. All right. There we go. All right, next question. Wait. So this one, it's really simple. Just as before, as we square rooted, we divided first and then square rooted, we can square root the numerator and the denominator separately. So the square root of 1 is 1. In other words, the 1 times itself gives you 1. So it's its own square root, it's its own cube root, its own quadruple root. Square root of 1, or whatever root of 1 is just 1. The square root of 81 is 9 times 9. So square root of 1 is 1. Square root of 81 is 9. That's it. There's no radical left over. Some people are still trying to keep the radical there, the square root symbol, but we're performing the square root, so the square root's done. There's no square root now. All right. Moving on. So this one, it says use the product rule for square roots to find the product. So 7 times 2 is 14, and there's nothing we can do about it. I We can't simplify it. So that's just it. This one, though, 11 times 11 is 121, and the square root of 121 is 11. This is showing you that if you square a square root, which is what's happening here, they cancel. The square and the power, or the square and the root cancel out. So, let's see. This one's just showing you that you can add, say the sum symbol here, you can add square roots. So the square root of 2, we're basically counting how many square root 2's we have. We have 9 square root 2's plus 3, so it'd be 12 square root 2's. This one's a little more trickier because we can't solve it the way it's written. The 10 square root 7 is already simplified, but this square root of 28 is not. So square root of 28 is like 4 times 7. And this 4 is a perfect square. So that 4 will square root to a 2. And the 7 will stay behind. So now we have a like term. This is like the other term in the sense that we're counting how many square root 7's we have. So we have 10 square root 7's minus 2 square root 7's. 10 minus 2 is 8. That's how many square root 7's we have. So this one, it says estimate the square root round to the nearest integer. 79 is pretty close to 81. 81, the square root of 81 of which is 9. So this is pretty close to 9. It says round to the nearest integer, so 9 is going to be it. Integer is like a whole number. So it says nearest closest whole number. Closest whole number is going to be 9. Now it says to the nearest tenth. So 35 is really close to 36, which is a perfect square. The square root of 36 is 6. So this would be right below 36, which is like 5.9, because this is nearest tenth. I'm going to verify that with a calculator, though. So 35 square rooted is 5.91, so it'll just round to 5.9, so that's correct. Now it's asking for the nearest hundredth. So the square root of 3, this is going to be pretty close to 8, because 64 square root is 8. But they want nearest hundredth. So I could never, you'd have to, they have this process that you can use to figure it out, the nearest hundredth. But I want you guys just to use a calculator and be able to round to the nearest hundredth. So it'd be 7.94. Okay. Evaluate square root of 17 to the nearest hundredth. Using a pencil paper. Is the estimate value rational or rational? Irrational. Explain. Well, it's going to be irrational because it doesn't square root evenly. It's going to be slightly above the square root of 16, which is 4. So it's going to be, let's see, it's square root 17. Let's see what we get. So they went to the nearest hundredth again, so 4.12. 4.12. All right. Excellent. So we could spend more time doing it the way they do it. I'll show you what they have you do. So if they find the two, they chose 214 as their example. So this is really close to the square root of 14. This is just above square root of 14. So they're showing you here. This is between 14 and 15 here. Oh, sorry. This is really close to 15. 196 is the square root of 14. 225 is the perfect square of 15. So they do whole numbers. And then they're showing you that it's going to be between these two. So they're squaring. So you have to use a calculator. The way they're doing it, you have to use a calculator anyway. It's kind of silly. Or I guess you could multiply them by hand. That could work too. But they're basically having you kind of guess and check. It's a very long process. And I don't want you to put that much time into this. We got other things we got to worry about. So for this problem, just make sure you can round to the nearest hundredth. All right, so that's it for this Classwork 3. Because I went through this so quickly, I'm going to do Classwork 4 as well. So this is going to be Classwork 3 and 4. 4 also goes pretty quickly. right. So let's see, refresh here. Similar question. So this is a cube root, and a cube root's a little bit different because now instead of groups of 2, we're going to be doing groups of 3. So if we have 64, I already know that's 8 times 8. I'm choosing to do a wide tree because I'm not going to have a lot of space here and set myself up for a lot of space. So this is like 4 times 2, 4 times 2. But say I have a perfect square here, but this is not going to be a perfect square. This is going to be a cube root. So now I need groups of 3. Well, there's actually groups of 3 here. If you look, there's a 4 here, a 4 here, and then these 2's can combine to make another 4. So there are groups of 3 here. I could split these 4's out into 2's if one were inclined to do so. And then you could say, oh, I got groups of 3 2's right here, and a group of 3 2's right here. So either way, we're going to get the same answer. So I'm going to pull out the 2's. So if I pull out these 3 2's right here, pull out a 2, and then these 3 2's produce another 2, which is the same thing as having a group of 4's, because this will come back together to make a 4. So the answer will just simply be 4 for this one. And if I did that too quickly, we're going to do some more of these, so hopefully it'll make sense. Similar question. So this one is a negative 64. We already know the answer. The cube root of 64 is 4. If it's a negative, though, it'll be negative 4. Another way to think about this is what number times itself 3 times gives you negative 64. Well, 4 times 4 is 16. Well, negative 4 times negative 4 is still 16. And then 16 times negative 4 is negative 64. All right, let's do this one. So the cube root of 40, and I'll break this down. So I'm just going to do 40, or 4 times 10. You divide it however you'd like. 2 and 2, 2 and 5. So because it's a cube root, we're looking for groups of 3. There are 3 2's here. So those will evenly cube root to just a 2. And then the 5 stays behind as a cube root. So this will be our answer. So 2 cube root 5. Oh wait, where did I write? What did I come up with? Factor out of 4. 10. Oh, I know I did wrong. It's supposed to be a cube root. There we go. 2 cube root 5. Very important to have that cube root there. How does that work? All right. Let's do a similar question. So we're going to factor tree this out. So I see that this 405 has a 5 at the end of it, or a 0, so I know that it divides evenly by 5. And if you divide this by 5, 400 divided by 5, use a calculator. You can use the one that they provide. You get 81. Okay. Now 81 is a perfect square, but we're not going for squares. We're going for a quadruple this time. Like 9 times 9. And then each of those 9's produces or divides into 3's. Those are kind of rough looking 3's. All right, so there's 4 3's here. So that's 3 times itself, 4 times. So all this whole 81 is a perfect quadruple, and quadruple roots to just a 3. So we'll have a 3, and then that 5 has to stay behind as a quadruple root. So make sure you have that 4 there. Okay. So when you do these, you got to make sure you use this one and not that one. This is a square root only. This is something other than a square root, like in this case, a quadruple root. So the 5 goes underneath because that stays behind. And we cube rooted that 81, so that comes out as a 3. All right. Quadruple rooted 81. Quadruple, as I say cube, quadruple rooted. All right. That's an easy one. All right, so this is we just did that. It's a 3. All right, next question. So there's 15 to go here. So this one's kind of interesting. This negative exponent, normally, say 4 to the 3rd power, is the same thing as repeated multiplication. So 4 times 4 times 4, which would be 64. That's 16 times 4, which is 64. However, when you put this negative up here, it's no longer repeated multiplication, it's repeated division. And so if you divide by 4 3 times, it's the same thing as dividing by 64. So the answer is going to be 1 over 64. But notice how my 1 over 64 is not negative. This just means that we're going to be dividing a bunch of times. It means literally that instead of multiplying repeatedly, we're going to be dividing repeatedly. So that negative in a way flips it into the denominator. Conversely, if you had 1 in the denominator but was also negative, it would flip it into the numerator. So we'll kind of see what that looks like. Oops. Press enter before I got that 4 in there. There we go. All right, so this is a good example. So this y to the negative second, this part, that y to the negative second, will flip into the denominator. But the x to the 6th is not affected by that negative 2. So the x to the 6th stays in the numerator. The y to the second falls into the denominator. This one, that we have 1 in the denominator, is going to flip it in the numerator. And so we'll get xy to the 3rd. And again, this exponent's not associated with the x and will not affect it. So the x just kind of hangs out on top. This one, so y to the 4th is 25 times 25. So 1 divided by 625. You could use a calculator to solve that. I just know that 5 squared is 25. 5 to the 4th is 5 squared twice, multiplied twice. That's 25 times 25. I just happen to know the square of 25. And it's in the denominator because it's repeated division. All right. So this one's interesting. This one has the negative in parentheses. So that means this is going to be negative 4 divided 3 times. So I'm just going to draw that out real quick. Negative 4 divided 3 times. So because it's being divided 3 times, it's the same as multiplying the denominator 3 times. So it's going to be a negative, because it's in, well, it doesn't matter. Either way, it's going to be negative because it's a 3. If this is a 4, it'd actually become a positive. If there was, if this exponent here was even, our answer would be positive. Because it's odd, we're going to have an extra negative floating. In other words, it's going to be 1 over negative 4 3 times. So for instance, if it was just squared, this would become 1 over 16 positive. Because we have this another one here, it doesn't have a partner to cancel with, so it'll become negative 1 over 64. So negative 1 over 64. Oh my gosh, not in the answer key. Here we go. Negative 1 over 64. Now that negative technically can be anywhere. It can be in the 1, it can be associated with the 64. This should work though, so I'll check my answer. Yeah. This one, however, even though it's being squared, well, negative squared, so it's dividing twice. This is 1 over 25. But it doesn't cancel out the negative because that negative gets applied after the exponent. So there's still a negative. That negative is just kind of hanging out. It doesn't cancel out because it's not the exponent takes place or happens first, and then the negative happens. So that negative happens after it gets divided twice. Because there's no parentheses. So this one has parentheses. So that negative is being divided twice. So 1 over 16. The negative does get canceled in this case because they're saying that that negative is part of the 4 and not just hanging out in front. This one's fun. So this little n to the 0th power, anything to the 0th power is just 1. So this is really just 1 times 2h. So 1 times 2h is 2h. And this just flips back in the numerator. So we have p to the power of 18. Instead of repeated division, we have repeated multiplication. This little negative negative 5 exponent only applies to the x, so the 2 will stay in the numerator, and that x, not cx, x to the 5th stays in the denominator, or gets put into the denominator, I should say. Repeated division of that x. Is that it? Last one? Okay, that's it. I hope that's informative. Again, if you have questions on any of these, please, please, please shoot me an email or ask me in class, however you feel most comfortable. I know I can be busy, not always available, so that's what these videos are for, that's what these questions are for, that's what these walkthroughs are for. Try to help explain stuff. You can click through them. It becomes like an open textbook, right? So if I'm not around, I think I glitched it out. Okay, it's weird now. I made it weird now. Anyway, so I hope that's helpful. Please ask questions. Please ask questions of those around you. Ask me. That is the best way to survive in any math class, is asking lots and lots of questions. Till next time.